In this video, we're going to delve deeper into the inverse trigonometric functions. Remember, we've a couple times used things in our calculator like sine inverse of 0.3 or cosine inverse of 0.7. We were trying to find reference angles in triangles using these functions. And that was fine, we got our answers, but now let's try to understand what's going on, where these things even come from. Before we talk about the trigonometric side of this, I want to remind everyone about a couple of facts about functions in general and how to find inverses. So if I took the function, I don't know, f of x equals 2x. This is a function that doubles whatever number you put in. If my goal was to say, okay, my function doubled the input, how do I get back to the original input? My inverse function would be the one that just halves whatever is inside. So if you were to do both of these functions, you always get back to your starting point. So you take a number in, if you first double it and then you halve it, you get back to the original value. And it doesn't even matter which order you do it. If you take a number and you take half of it and then you double that new answer, you're also going to get back to the original number. So these are what are called inverse functions. On the other hand, if you had a function like f of x is x squared, there in fact is no inverse function. You might think, well, what's the opposite of squaring a number? You could say square rooting, and this would be okay for some numbers. If you took, for example, the number 5 and you square it, you get 25. If you then square root 25, you get back to 5. However, if you start with a negative number, say -3, and square it, you get to 9. And if you square root 9, the only answer to square root of 9 is +3, and we did not get back to the starting value. So some functions have inverses, great. Some functions do not. And it's actually a really quick test to see whether a function will have an inverse. And it's called the horizontal line test. It checks whether a function is 1 to 1. This is the phrase here, 1 to 1. And the idea is if you draw a horizontal line, and if it ever crosses the graph more than one time, that means you're not going to be able to have an inverse. It simply cannot be done. If you compare that to the graph of y equal to 2x here, no matter which which horizontal line you draw, you're never going to cross it more than once. Therefore, there is an inverse. Okay, so the main result from algebra we need to recall is that if a function is 1 to 1, there is going to be an inverse function that will get us back to our starting point. Now, we have a really big problem, though. If I draw a rough graph of sine here, I'm not going to worry about being too exact accurate, just to give an idea. Looks something like this. And if I want to say, okay, is this 1 to 1 function? Does it pass the horizontal line test? And you see it fails the horizontal line test spectacularly. Not just a little bit, not just, having 2 points with the same y value like in the parabola there, y equals x squared. Instead, it's going to cross infinitely many times. What that means is this simply will not work. You cannot have an inverse function for sine. Mathematically, it cannot be done. However, we have been using an inverse function for sine already. You might say, wait a second, you just told me it can't be done, but we've already been doing it. What's going on here? And the answer is we find a way to cheat. And so here's how we're going to cheat. So let me go ahead and get rid of my graph here because we just saw it fails the horizontal line test. And let me go ahead and draw it one more time here. I'm not going to keep drawing forever. I'm just going to draw a little bit. And even if I draw this little part right here, I fail the the horizontal line test. But what we're going to do is we're going to take just a piece of this graph. We're going to start erasing things until we don't fail the horizontal line test anymore. So I'm going to erase things over here. I still fail the horizontal line test, so I'm going to erase some more. Still fail the horizontal line test. I'm going to erase some more. And as soon as we erase this much here, to where my graph starts at negative pi over 2 and ends at positive pi over 2, this piece of the graph passes the horizontal line test. What that means is that this piece of the graph does have an inverse function. And that's what the inverse function is that we've been using in the past. It's just this piece of the graph. And so what that means is that the angle that you get for sine inverse is always between negative pi over 2 and positive pi over 2. Because if you were to go even a little bit past this, go a little past pi over 2 here, it's going to dip down. And as soon as it dips down, you're failing the horizontal line test. So we can't go any further on the positive side except for positive pi over 2. Can't go any further on the negative side, negative pi over 2. So you're allowed to use sine inverse function as long as you understand that the angle you get as the answer is always something between negative pi over 2 and positive pi over 2. Previously, we only used inverse functions to find reference angles, and you may recall the rule when we were doing that is we need to have only positive values when you put input to sine inverse, and that's basically saying that this right here is the part of the graph we're looking at. Plug in positive values, you get the answer between 0 and 90 degrees, and that's going to be your reference angle. If you had plugged in a negative value into sine inverse, you would have got an angle that's between 0 and negative 90 degrees. That is not the reference angle anymore. On the other hand, if you knew your angle was in quadrant 4, then you could use sine inverse because quadrant 4 is between 0 degrees and negative 90 degrees. All right, let's go draw the unit circle up here. Quadrant 4 is from 0 to negative 90. So if you did sine inverse and got an answer, it would be in quadrant 4. But the thing is what if the value you're looking for is not in quadrant 4, it's in quadrant 2 or quadrant 3? That's why we didn't just do sine inverse of whatever we had, and instead did sine inverse of the positive number, found a reference angle, and then use the reference angle to translate to whatever quadrant you want it to be in. So I would still continue on just doing sine inverse of positive numbers if you can help it, because if you do sine inverse of a negative number, you're only going to get the quadrant 4 answer, and you might not want that answer. You might want a different quadrant. If I continue on here to cosine, it's the same idea. I only want one part of the graph. However, it's going to be a little bit different which part I take. So if I draw the cosine graph here, it looks something like this. Once again, if you draw the horizontal line, it's going to have infinitely many crossings. It fails the horizontal line test. But if I try to erase down to, like, say, negative pi over 2 to pi over 2, if I continue that there, you see, even at the beginning here, I'm failing the horizontal line test right around 0. So we're not going to do that. We're going to start at 0, and we're going to go all the way over to pi. So this is the piece that we can use for cosine. We can do a cosine inverse of y is always between 0 and pi. So there is a difference between sine inverse and cosine inverse. Sine inverse, you're going to get the answer between negative 90 degrees to positive 90 degrees, whereas cosine inverse is going to give you the answer between 0 and 180 degrees. That means your cosine inverse is going to give you an answer somewhere on the top of the unit circle. What that means is if you're trying to find angles that are in quadrant 1 or quadrant 2, feel free to use cosine inverse without any issue. But if you want quadrant 3 or quadrant 4, you're not going to get the answer from cosine inverse. So I guess the moral of this is that even though you are now able to do cosine inverse of negatives and figure out what the answer is based on these two properties, I wouldn't recommend doing it. I still think it's a better idea to do cosine inverse of a positive number, get the reference angle, and then use the reference angle to translate to whatever quadrant you're interested in. Finally, the tangent function, if I draw that, it's going to turn out that it's going to have almost the exact same range as the sine function here. Looks something like this. So the tangent graph should take that and repeat over and over again. But if you were to repeat it, let's say right here, you're going to fail the horizontal line test, so we get rid of all the other copies. We just keep the copy right in the middle, and then the inverse of tangent here is always between negative pi over 2 and positive pi over 2. Now I said it's almost the same as sine, but what I've written here actually looks like it's the exact same as sine. And the difference is, for sine, you can actually get the answer negative pi over 2, or you can get the answer pi over 2. So they include those ending values there. Whereas tangent, you'll never actually be able to get to pi over 2 or negative pi over 2 because of those vertical asymptotes. And so here it includes the same interval but does not include the endpoints of the interval. So that's why we have parentheses on these. So these are good facts, and if you're ever trying to deal with inverse functions, you want to recall where the angles are going to be located for sine inverse, cosine inverse, and tangent inverse. However, it's not as important, because if you just try to do the inverse of a positive number, you can convert it to whatever quadrant you want using reference angles. Now you might say, these are three functions that have inverses. What about the other ones? What about secant, cosecant, cotangent? And yes, you can do the same thing. You can draw a piece of the graph that satisfies the horizontal line test. You can create an inverse, but we hardly ever do that. We hardly ever try to figure out what's going on with those ones. And let me give an example. Let's say I want to do secant inverse of phi. That means I want to find the angle, I want to find the theta. That means that the secant of theta is going to equal to 5. That's what the whole idea of inverse functions are. Well, if secant theta is equal to 5, that means cosine theta is 1/5, because cosine is the reciprocal of secant. And that means that I can find the angle theta by doing cosine inverse of 1/5. So if you ever have to actually do a secant inverse or a cosecant inverse or a cotangent inverse, you're just going to use your reciprocal identity, convert it to either a sine, cosine, or tangent, and then use that on your calculator to get the answer. That's why you don't have inverse secant button on your calculator. You don't have inverse cotangent button on your calculator. They don't exist on there because they're not necessary. You can just use the reciprocal identities to get the answer anyways. Now the last thing I want to show you on this section here is trying to simplify a crazy expression like this, because they do come up sometimes and it can be important to be able to work this out. And notice that there's no number in there, so we can't just put it in our calculator and get an answer. We have to use our trigonometric knowledge to write an expression for the answer. Here's how it's going to work. So I know that I have this cosine inverse of x inside. Okay, so if I have cosine inverse of x inside, that means I'm trying to find an angle whose cosine is going to give me x. Well, I'm going to rewrite x as x over 1, because cosines are fractions, and by SOHCAHTOA, that means I should have a right triangle here, where if this is my angle theta, my adjacent should be x, my hypotenuse should be 1. CAHTOA. So CAHTOA, adjacent over hypotenuse. And if I do that, I can use Pythagorean theorem To solve for the missing side, it's going to be the square root of 1 minus x squared. And once I've figured this whole triangle out, now I can answer this question here. Sine of cosine inverse of x, that's sine of the angle theta, and from this triangle, it's opposite over hypotenuse. And so the answer to this expression is the square root of 1 minus x squared. Notice again, calculator is not really going to help you on something like that. And it really comes down to drawing your own right triangle and then using that right triangle in SOHCAHTOA to answer the question what they're looking for. These ones, in my experience, have been a big challenge for most students. I wanted to give you at least one example in the video here, and you should practice things like that for the future.